Okay, so it's time for a discussion of Chapter 3, which is our final chapter of this course, Stoichiometry, Ratios of Combination. It's a rather lengthy chapter, and it's an essential chapter to the understanding of how we deal with calculations in chemistry. So I'm going to break this chapter up into more than one video. So you won't see me going through every section in this one, and stay tuned for other videos for this chapter. So let's begin with molecular and formula mass, which is section 3.1. Molecular and formula masses is an introduction to the idea that we can measure masses in order to count the amount of material, to measure how much material we have. So here's the way we're going to start with this. The idea here is that each element has what's called an atomic mass. So for example, hydrogen has an atomic mass of 1.008 atomic mass units, AMU. Oxygen has an atomic mass of 16.00 AMU. And so the water molecule, if you try to calculate the mass of one, or the mass of water, you would take the number of hydrogen atoms, which is 2, and multiply that by the atomic mass of each hydrogen atom, and then add that to the atomic mass of one oxygen atom. So 2 times 1.008 plus 16.00, both in AMU, and you get 18.02 AMU. Now, take a look at the number of significant figures in this calculation. Notice that we're adding, right? We're adding the atomic masses of hydrogen to that of oxygen. Oxygen, based on the numbers we're using here, which we would get from the periodic table or some other source, oxygen has a number that goes out 2 digits past the decimal point, whereas the hydrogen has a number that goes 3 digits past the decimal point. But our rules of significant figures are that if you're adding or subtracting, your answer can't have more significant figures past the decimal point than any of the measurements you're adding or subtracting. So since the oxygen only goes out 2 digits past the decimal point, the answer can only go out 2 digits past the decimal point. So we round it to 0.02 instead of having it be 18.016. Okay? Now that depends on your source of data. If you looked at a periodic table that had more sig figs, you might be able to find that oxygen's 15.9994 AMU. You can use that value. But if you're using the periodic table in the textbook, the eBook, then the oxygen only goes out 2 digits, so your answer would go out 2 digits. Okay? So that would be called the molecular mass. That's essentially a measure of the mass of one water molecule, H2O. There's some other terms you should be aware of. Molecular weight, that's the older term. We don't tend to use that as much, but you're definitely going to see it out there. The reason for that is that we prefer to use the term mass as opposed to weight, because weight is really a force. It's really how gravity acts on a mass. But chemists never used to worry about that kind of thing, so we called the molecular weight. It's not a big deal at this point. There's another term called formula mass. Formula mass is essentially molecular mass, but some substances, ionic compounds, they don't exist as individual little molecules. So water is a molecular compound. It exists as a little molecule, H2O. But sodium chloride, salt, table salt, does not exist as individual NaCl molecules. It exists as a matrix, as a large substance of large numbers of ions bound together. So we can't call it a molecular mass because it's not really a molecule, so we call it a formula mass. Okay? So formula mass is calculated the same way molecular mass is calculated. It's just used for ionic compounds. Okay? So here's a sample problem. Calculate the molecular mass or the formula mass, as appropriate, for each of the following compounds. Propane, which has the formula C3H8, lithium hydroxide, LiOH, and barium acetate, BaC2H3O2, 2. Look at all those parentheses and brackets and subscripts. So with this one, what you would do is you would use the periodic table and you would look up the atomic masses of each of the atoms in that substance and then add them together. So just a pointer on this one. For propane, C3H8, there are 3 carbons. That little subscript is giving you the number of carbon atoms, so there's 3 carbons. For H, there are 8 hydrogens, C3H8. So you would take 3 times the atomic mass of carbon and 8 times the atomic mass of hydrogen. LiOH is pretty straightforward. There's 3 elements, but there's only 1 of each. 1 lithium, 1 oxygen, 1 hydrogen. Barium acetate is more complicated because of all these brackets. So the reason the square brackets are there is just to tell you that that's the formula for barium acetate. The rounded parentheses are there to tell you the number. So in this formula, there's 1 barium, but there's 4 carbons. Why 4 carbons? Because it's C2, but outside the parentheses, there's another 2. So 2 times 2 is 4, so 4 carbons. What about hydrogen? There's a 3 subscript, but there's a 2 outside the bracket, outside the parentheses. So that's 6 hydrogens, 3 times 2. And then oxygen, 2 times 2. So anything inside the parentheses is multiplied by the number just to the right of the parentheses. Okay, so 4 carbons, 6 hydrogens, 4 oxygens. Take a look at the solution here for the barium acetate. Barium has an atomic mass of 137.3 AMU. Carbon has an atomic mass of 12.01, but there's 4 of them. Hydrogen has an atomic mass of 1.008, but there's 6. And then there are 4 oxygens, 4 times 16.00. Notice the answer only goes 1 digit past the decimal point. Why? It's the barium. Barium only goes 1 digit past the decimal point. So you pick the atomic mass that goes the fewest digits past the decimal point, to the right of the decimal point, and round your answer to that one. So if barium had said 137.31, you would go 2 digits past the decimal point, but you're going to stop at 1 decimal point because of the barium. So try your practice problems. That's a good problem. Try your checkpoints. Very straightforward questions. They're easy to calculate. You want access to a periodic table. If you memorize the atomic masses of the periodic tables, I'll be impressed. Everybody would be impressed. But you don't need to do that. Just grab yourself a periodic table.